Bismillahirrahmanirrahim. Welcome to the course on VLSI design. So the course has two components. One is the theory part, which is 3 credit hour, and then we have a lab part, which is 1 credit hour. So let me explain the title a bit. So VLSI means very large scale integrated circuits. So it refers to the kind of electronic circuits that you can find inside, for example, a microprocessor or a microcontroller. These are very large scale integrated circuits. In fact, these circuits have billions of transistors inside a very small area. If you open up your desktop computer and look under the fan, you will see the microprocessor. And if you go on the Google and check out its specification, you will be astonished to know that your computer microprocessor has millions and billions of transistors inside it. So how can this complex circuit be designed? So it's very complex circuit. So how can we deal with this complexity? So in this course, we will teach you how such complexity is handled. Of course, this cannot be handled by humans. So we have very smart and sophisticated set of software tools that are able to map billions of transistors inside the chip. We will talk about these tools in this course. Okay, but first, what are the prerequisites? So the prerequisites are, you should have a basic course in digital logic design, which I think you all have taken. Then you should have electronics 1 and electronics 2. Maybe electronics 1 is enough, but if you have taken electronics 2, it's good. The course instructor is me, and here is my email address, anisullah@utpeshawar.edu.pk. And this is the course catalog, which describes the sort of story of what's inside the course. Of course, I do not expect you to understand this at the moment, but let's analyze some words which are important and which will keep up coming again and again in this course. So the first word that I want you to focus on is CMOS. So this is complementary metal oxide semiconductor. So complementary means opposing, and metal oxide semiconductor, why is it called metal oxide semiconductor? Because these CMOS transistors are designed with a layer of silicon dioxide and a metal above. So these are called CMOS logic. So we have, like, for example, I think that you will not be able to understand this fully, but let's try to. So for example, this is a NOT gate in CMOS logic. So, for example, this is called NMOS, and this is called PMOS. PMOS has a bubble here. So it's called complementary because it has both P type and N type transistor. How this is a NOT gate and how it works, we will discuss in the course. So all the gates in CMOS technology have this sort of nature that they use complementary transistors. So this is a NOT gate. If we take an AND gate, it will also have PMOS and NMOS combined in a certain way. If we take a NOR gate, it will again be composed of PMOS and NMOS in certain configuration, maybe in series and parallel, or maybe both. So we will look into how we can develop these kinds of gates from CMOS transistors. And by gates, I mean the gates that you would study in your DLD. Then the second thing is this word which will keep fabrication. So what fabrication essentially means is that you have a silicon, which is you get it from nature and you process it, and fabrication is the process of mapping your circuit, which consists of your logic gates, onto a physical chip. So in this course we will study how it is possible to fabricate such kind of ICs or chips. What are the rules? What are the rules for these fabrication processes? How they are interconnected, how we simulate, how we test, how we design for low power. So then, for example, we will also study how fast we can clock the circuit. What is the maximum frequency? So you are always concerned about the maximum frequency when you buy your computer. So you used to think that Pentium 4 is better than Pentium 1 because it has a higher clock frequency. Then there is another thing or matrix, that is power dissipation. So as like your computer, your smartphone is also an embedded computer, and the power dissipation is a very important aspect for embedded systems. So we will talk about how we can reduce the power consumption, and all these things are possible thanks to the CAD tools. So CAD means computer aided design. So as I told you before, the CAD tools are responsible for taking your design. For example, it may be a CPU design and mapping it onto silicon. All these steps are performed by a software, and these software are called CAD tools, and we will study certain CAD tools. So all this complexity is handled by these CAD tools. And so just to summarize, our goal is like this one. For example, we take a certain problem It may be, for example, an algorithm, okay, and you want to add, for example, you want the algorithm for factorial. So you have the factorial algorithm, for example, in C or C++, okay, and you say, I want to design a chip that can implement this factorial algorithm. So you will inside during the course, what are the steps that are required for taking this algorithm and mapping it onto silicon, okay. So the course is designed to give students an understanding of different design steps required to carry out a complete digital VLSI. So we are talking about digital VLSI, okay, not analog. So this course is not about analog VLSI circuits. This is about digital VLSI circuits. Then we have certain books. There are 4 books here, but I don't think I will follow a book specifically in its entirety. So maybe I cover some topics from one book, some topics from other books, and maybe some topics you cannot find in a book. But whenever I will cover from any of these books, I will mention the sections. Okay, so the first one is Introduction to VLSI Circuit and Systems, and the second one is Digital Integrated Circuits, a Design Perspective. Then there is Digital Integrated Circuits from VLSI Architecture to CMOS Fabrication. And the last one is CMOS VLSI Design, a Circuit and Systems Perspective. Okay. So, although I have talked about the course, these are the course learning objectives. So be able to understand the mathematical methods and analysis of CMOS circuits. So all the equations for writing the circuit analysis, for example, for current, for voltage, for all these things, you should know how to mathematically find the equations for them. And then we will develop models, okay. So the models are necessary to analyze circuits using standard techniques. So what a model do? A model hides the complexity of the physical systems. For example, in this case, our physical system is a transistor. So for example, you know that a transistor is something like this. A field effect transistor has a source, it has a drain, and it has the silicon layer, and then we have a gate, okay, and this is our substrate. So this is the physical system. You see, we have a PN junction here, we have a PN junction here. So whenever there is a PN junction, there is a capacitance. So we have capacitance here, similarly capacitance in every junction. So what a model does, it gives us a simple circuit that is equivalent to our FET, and which we can analyze which we can analyze more easily. So we will talk about the models for MOSFETs and for CMOS circuits. Be able to apply technology-specific layout rules for placement and routing. So what is placement and what is routing? So you see there are many transistors inside a chip. As I told you that in a Pentium 4 processor, for example, if I remember correctly, it has 40 million transistors. So how you place those 40 million transistors inside a very small area? Okay, so placement is about where on the, for example, this is our chip, where we want to place our transistor, for example, here or here, and how we want to connect those transistors. I mean, the wire runs like this or like this. This is called routing. Okay, for example, this wire is shorter compared to this wire. So how you connect up these transistors will affect your speed of your circuit. Okay, so but normally these transistors are connected by the software, and that software is called a router. And similarly, the placement is done automatically by a software that is called placer. You can affect the behavior of placer and router. You can tell the placer and router, okay, I want this kind of routing, I want this kind of routing, I want this kind of placement. You are able to tell the router what are your preferences, but actually the placement and routing are done by softwares. We will study the characteristics of CMOS circuits. We will design for certain objectives. So the design objectives are, we want the area to be reduced, we want the speed to be increased, and we want the power consumption to be reduced. So we want to design circuits, but we want to design for certain speed, for certain area, and for certain power consumption. Okay, so we will cover two kinds of circuits, combinational and sequential. Again, these you know very well from your digital logic design course. Okay, but in your digital logic design course, you were doing all the things at this kind of gate level, and in this course we will go inside the gates. Okay, so describe the general process steps required for processing of CMOS circuits. Okay, and then we will study, for example, flip-flops, latches, and adders, multipliers, ROMs, and strings. So these are the course learning objectives. And what are the course learning outcomes? So these are CLOs. So this is the list of CLO. We have 3 CLOs. So the first one is explain the logical characteristics of MOSFET. Again, MOSFET means metal oxide semiconductor field effect transistor. So if you remember from your basic electronics course, you studied BJTs, bi-junction transistors, and MOSFETs. So we are only concerned about MOSFETs in this course and not BJTs, because all the digital systems, whether they are your smartphones or your PDAs or laptops, they are based on this MOSFET. They have low power consumption and they have better capabilities than BJTs. So we will develop techniques for digital networks, translate the CMOS integrated circuit into silicon, and demonstrate the knowledge of electronics for MOSFETs and their interconnects. So this is the first CLO. Okay. And the second is to analyze it, study the mathematical methods and circuit analysis techniques, and for what? For current, voltage, and parasitics. We will talk about parasitics. Parasitics are those capacitances that I drew between PN junctions, and CMOS circuits along with optimization for switching speed, layout, power consumption. The third one is analyze the characteristics of CMOS circuit construction, classify and design state-of-the-art CMOS technology. Okay. Hopefully, when the course goes on, we will understand more about the CMOS. So we have the learning outcome assessment plan. We will have 4 assignments. We will have 4 quizzes, a midterm and a final term. This is the outcomes CLO mapping to standard TLOs, and quizzes will be 10%, homework assignments 10%, midterm 20%, final term 60%. So this is the weekly distribution of topics. So in the first week, we will introduce the course in a very generic way, and the main goal is to motivate you about the course and what you should expect during the course, the basic concepts. Then in the next 2 weeks, we will dive deep into the MOSFET, and we will study how we can use the MOSFET to implement Boolean functions and to construct different kinds of gates from CMOS logic. And we will study about transmission gates and things like that. Then we will move, so this is like the logic circuits, and then we move to for logic circuits for simple gates. Then we move to the physical structure. So how now we are moving into closer to, near to silicon. How we are able to translate this logic gate into a physical silicon structure. Then again, that is continued. We will talk about fabrication and design rules. So just to tell you, this fabrication processes are carried out in what are called fabs. Okay, and these fabs are very, very expensive. These are billions of dollars to establish a fab. And inside these fabs, they take the silicon in raw form and they pass it to several steps to convert it into wafers. Again, we will see inside the course what are wafers, and then they use light. They use light as a source for what? For etching circuits. So you have like a circuit pattern. So you have a circuit pattern, and on this pattern you throw some light, and this light goes onto silicon, and this pattern is drawn here. So this is like a very crude way to tell you how it works. Of course, inside the course we will see the pictures and all the things you can understand better. Then we will discuss the MOSFET electrical characteristics, the capacitors inside the MOSFETs, the energy band, threshold voltages, and all the regions, cutoff, linear saturation. In week 7 we'll have a midterm exam. Then MOSFET electrical characteristics will be continued. So we will study the RC model and scaling theory. So you see along the way the transistor is getting smaller and smaller. So we will see what are the factors and that are keeping this momentum. Electronic analysis of CMOS logic, so DC and switching characteristics, power dissipation, and all these. Then we will go to design for speed. So for example, we will ask what is the maximum frequency of a circuit that is designed, or let's put it another way, can you design a CMOS circuit for 100 kilohertz? Okay, so we will answer questions like these. Then we will go to the advanced techniques in CMOS logic, which addresses some of the problems. Okay, in simple approaches, we'll talk more and more detail about this, and then we will study combinational circuits, several combinational circuits, and several sequential circuits. So what is the approach in the course? We start from the transistor, okay? Then we say how we can combine transistors in better way, okay, such that it gives us a good speed, it gives us a smaller area, it gives us a little power consumption. And then we build some circuits. For example, we can build combinational adders, we can build multipliers, all for the sake of these goals, to see how can we design different combinational and sequential circuits, for example counters. And the last 2 weeks are dedicated to memories. So again, different kinds of memories, for example how we can construct ROMs, how we can construct RAMs. Okay, so this will be the last 2 weeks, and then we will review the course, and that's it for the course description file.